So it's crooked.
It's all good. I think reality is crooked. So the camera's just doing its job.
Because we're not lying.
Quiz on chapter 8, basically.
Nothing makes sense in our
So what I'll do, I'll have the formulas up on that quiz just like before. So it's going to be, like the x bar plus minus z, x bar plus minus t, s, then the p hat stuff, good old p hat. When you're out on the boat, all you got is a hat. And then you got the n formulas too, for when you want to know a certain sample size to achieve a certain error. Does that sound familiar? I call it a feasibility formula. So we have about 8 billion people. Well, shit, let's kind of rein in our error bound so we can talk to some reasonable number of people. Okay. Any questions from homework stuff? Okay. Because some of it does get a little weird. So I'm always a little worried when nobody has questions about the weird shit. All right. So we're going to do some examples. We're going to do 2 examples together, hypothesis test, and then I'll let you guys work on 2 on your own, amongst yourselves. Right? So let me give you guys this one. Is this the one I want to do? Yeah, sure. Am I sure about that? No, I'm going to do this one. Give you the hard one to do it right. Alright, so let's do this one. Yeah. Oh. Sure. Make sure it turns on. You guys had a good Halloween? I don't think I've seen you since then.
Sorry.
Huh?
You were
We were here Wednesday, but Halloween was Tuesday, that's right. For some reason I thought it was Thursday. I think we just celebrated a few times, so I kind of lost track of when it actually was supposed to happen. We still got, oh my god, I still got so much candy. Oh my god. Stole from the kids, they don't know.
You're going to throw it to the crowd?
They don't know. They're happy they had some candy. Okay. So, being all nice here and bolding certain important information, which I will not always do, obviously. So read through this if you haven't already. So what about time, how old they are when they have their first baby? Hopefully you understand this does not include people that did not have a baby, because then You have to include a very old age if they lived so a long time, and then that would make the mean all freaky. This is people that had a baby. Okay. So the first thing you're scanning for, and this is sort of like when I teach word problems in algebra. Hopefully you guys understand this is not a word problem, right? But a word problem in algebra, what you do is you scan through and you don't first look at any of the math stuff. You're just looking for who are the players so I can assign them variable names. When we read through this, the very first thing the only thing we care about really is what the hell the claim is, because that's what gets things started. So what is the claim that's being made?
The mean is greater than.
Is there a claim being made in this problem? Yeah.
Average has increased.
Yes, average has increased. I love it. So the mean is greater than 24.81. We believe the average has increased from that 24.81. So the claim, it has to include some kind of a number at the moment. We're not comparing two populations. We're saying that we think that the population mean now is greater than it used to be. Now, what number will never ever show up in this first step is any sample information. Because in real life, we're going to have a hypothesis, and then we're going to go take a sample. I think this. Let's go talk to some people to find out. So that 25.29 would never show up here. It doesn't make any damn sense to go, I think it's this because I can see the future with this. You should probably make money some different way. So there's always going to be a claim about it's changed or everything's more or less than something that was before. Some number's got to be involved there, not from the sample. Which one is that going to be? The null or the alternate for the easily offended amongst us? Or the ho and the high for everybody else? Is that going to be the ho or the high? What's got to be true about the ho? It's got to have equal sign. I love it. Does it have an equal sign? No. So it's a high. I like it. And everybody said hi. You're right. So make sure everybody's on the same page. Everybody must say. So mu greater than 24.81. So what's the ho then?
Mu is greater than or equal to.
U is equal to 4.8.
Mu, what's the opposite of greater than? Less or equal to. Now in the book says the ho is always equal to, but then and there's another example, they actually have something that's different than just equal to there. Me, it's just these are always the opposite of each other. To me, if I see ho is mu equal to, then the H1 should be mu not equal to. That's the only thing that really makes sense there. These should be opposite statements. And that's why if we can say one looks wrong, we can automatically say the other one looks right. Because they're opposite statements. So is this going to be a one or a two-tailed test? Which one?
One.
Yeah, how do you know it's going to be a one-tailed test? Because where do I want my sample to end up? To show evidence that it's greater than. Remember, the high is the one you can show evidence for. I need my sample to show up that way, right? So I only care about one side. So if my H1 said mu not equal to, how can you be not equal to something?
Everything but.
It could be greater.
Or? Then it would be two-tailed, because then either way helps me. Right now, what's the only way that helps me? Up. One-tailed test. Let that be easy. All right. In fact, normally, if you can't tell, it's a two-tailed test. And we'll do a two-tailed test. I'll let you know already on the other side. And we'll see why it's hard to tell that sometimes. It's kind of buried. But if you see a word like increased, we think it's less than. We think more people, okay, that's an automatic one-tailed test, one way or the other. So it's going to be a one-tailed test in this direction, right? Because I want greater than. Now in part B, you always have to be able to tell me two things. Do we use Z or T scores or nothing? And I like to people like, nothing. Next.
Z-squared.
Yeah, all right, well, why Z scored?
Yes, standard deviation.
Which standard deviation is known?
Population.
Yes, sigma known, and from the word known. And something even more basic than that. What should always be written first. How do we know it's normal?
More than 30.
Because the sample size is it's 264, yeah, way more than 30. N equal 264, more than 30, so it's normal enough. Check. So in order to do anything, it has to be normally distributed. Either it's got to say it, or the sample size has got to be big enough. And then, how do you differentiate between Z or T? Now that we know we can do something, it's which standard deviation do you know? And some people just kind of hear that and go, if I know a standard deviation, it's a Z-score. What? You got to know a standard deviation for either one of those freaking things. It's just which standard deviation do you know? So why were T-scores invented? To torture students, but also, why were T-scores invented? To cover our ass for when we only know the sample standard deviation. That's why they were invented. So that's when you use them, when you only know S. But we know sigma, so we can use freaking Z-scores, yay. I like it. All right. Rejection region, using a level of significance. What symbol do I use for this, by the way? Yeah, little fish do. Alpha's 0.01, so one-tailed test. We're using Z-scores. So where do I look to find the Z-score that I want?
Bottom.
Yeah, I look at the T-score chart, like a crazy person. And why are all of us crazy people okay with that? Because T-scores are needed for when I have just a standard deviation of a sample. But when my sample gets really freaking large, I can use Z-scores. I don't need T-scores anymore to cover my S. Because then I feel pretty good about the S. I really want that to make sense. That's why the T-scores get smaller and smaller, and then they eventually become the Z-score. Because if I have a large-ass sample, that's basically sigma then that I get. Yes, ma'am?
So you can use the Z-score chart?
You can totally use the Z-score chart. I love it. I'm trying to get you guys to realize that this is actually a little more useful for certain values. Now, when can I not use this? When I have an alpha that's not one of these. So I have a one-tailed test. What's alpha? What's alpha?
2.1.
Yeah, 0.01, right? Alpha's 0.01. One tail, 0.01. Kabam. So if I said alpha was 0.03, oh shit, I got to use the Z-score chart. Of course. I love it. Can you still use the Z-score chart right now if you want? Yeah, of course. You can do it the old-fashioned way, right? Let's make sure that people at home can see what's going on. Jeff. Poor little people at home. Okay. All right, so what do you guys get? 0.01. One tail. Z-score is going to be at the bottom. 2.326. Sure. So the whole idea, and I think, hopefully, let's get this. If the mean is in the right place, if the mean from the claim is correct, is in the right place, then any sample I take should be close to it, right? And now in this problem, we're defining close to be less than this, right? Because that idea is not 2 anymore, it's more specific now. So for some reason, this is the number that we picked for this. It depends on the problem. Are you guys kind of with me? So if I got a sample that's here, we can look and see what the probability is that the mean is in the right place, but it's going to be so low that what's more likely is that ain't where the mean is. The mean's actually up higher. So if I get a sample right there, if I got a sample right here, then what's true is that's not where the mean is. The mean is actually over there somewhere maybe. Because I just did something that's so unlikely if the mean is the 24/1 that it must be actually higher than that. And that would make this area more likely. Right? Please let that make sense. So assuming, we always go into these hypothesis tests, assuming that the mean is 24.81. Let's see what we do. Let's see if the sample is just so crazy that, whoa, that's evidence that it isn't 24.81. So this step, we just set up how far away is far away enough to show evidence of something. And then the next step, of course, is how far away did our sample get? Okay. So just like before, when we said unusual started at -2 or 2, and outside of there was unusual, right? And that would mean evidence that something was weird. Well, here we're being a little more precise. Not just changing the number, but also paying attention to just one side or the other possibly, right? So now we're saying unusual would be outside of this. If I get a sample in here, that means that it's probably not 24.81. It's probably higher. It's evidence that it's actually a higher mean. So again, if I thought, going back to the first example I gave, if I thought the average age of Grossman was 40, and you go take a sample of 90 students, and you get an average of 25 or something, you with me? And I'm like, well, that would be unexpected. If I think it's 40 and I get a sample of 25, is that unexpected for me? Yes. Then I'm like, oh shit, my initial assumption must be wrong. My assumption of average of 40 must be wrong. What's more likely is the actual average is lower. Now, do we ever actually prove that? No. So this is where you got to get over this. This is just like court. This is just like real frickin' life. It can only show good evidence, strong evidence. There's always a chance for wrong. In fact, that 0.01 is a chance for wrong about rejecting something. You got a 1% chance of being wrong about rejecting something, and I can live with that. That's pretty good. Okay, maybe. So do you see how if rejecting something at the wrong time was bad, then I'd want to make alpha really small. So don't make that mistake too often. That's why we have different levels of alpha. Instead of just going out 2 standard deviations, we now go out whatever it is depending on how bad it is to make a mistake. Love you guys. Okay. So how do I say this in words? This picture, how do you say this picture in words? Why did I shade this in and what the hell? Let me start us off. If the sample I get is where? As a z-score where? If I go take a sample and I find one that's got a z-score where? Then I can reject the null. When? If I find a sample with a z-score of what? Or more than what? What does my picture say? If it's greater than 2.326, I'm in there. And we call this the rejection region. Guess why we do that? Because if I get in there, I can reject the HO. No idea why I'm saying it so extreme. Bam! So if my sample is so freaking far away from 24.81, and what is far away enough in this problem? 2.326. If it's more than that far, that many standard deviations away from 24.81, then shit, 24.81 can't be right. Okay. So if Z star is greater than 2.326, we can reject the null, support the high. If it isn't, then we fail to reject the null. We fail to support the high. So, what are we talking about? What can we use to talk about it? What's going to be far enough away to show evidence? How far away did we get? That's the steps, the first 4 steps. Let's see, what do we know from the sample? What's n? 264. What's x bar?
24.81.
No?
No.
What's the one we get from the sample?
25.29.
25.29. What's sigma?
2.85.
2.85. So what's sigma sub x bar? Remember, we always have to do this. Always a step in this is to find the one for a group of size whatever. In this case, 264. So we got to take the one for individuals, the old one, divided by the square root of 260 frickin' 4. Thank God. Somebody saved me myself. What is it again?
0.175. 0.175.
475? Okay. Is that what you guys are getting? Anybody else trying that out? Okay. So this step is this step D is the old step. This is stuff we've done before, but now we're using this to investigate something. We took a sample, we know how the samples are spread, the standard deviation there. Now we're about to see, based on that, how far is this sample relative to all the other possible samples. So Z star is my data, 25.29, minus this guy. Always this guy comes as the minus this, because that's what we're assuming to be the real center. Divided by the new standard deviation. Become a subject. Like 2.9. Maybe.
2.74.
Okay, I go with that. So that's Z star. Sure. Did we make it far enough away?
Yep.
Yeah.
Yeah, we're way the hell out here. 2.74. So really, please let this make sense. Assuming it is 24.81, then any sample, any good random sample, especially at 264 things, should be close to that if that's the real mean. Did we end up close to the 24.81? No, we're way the freak out at 2.74. So what's more likely, that we just happened to pick a sample randomly that ended up that far away, or that the real mean is not 24.81 anymore? What's more likely? I love you guys. You're like,
Former.
yeah, the mean is probably not 24.81 anymore. Now, I don't know if I've said this yet, because I don't think we did too much of this yet, but p-value, have I said p-value? Yeah, probably not. You're all like, dude, you're throwing on p-hats and shit, now you're talking about p-value. The p-value, I want this to make sense. The alpha, how does the alpha relate to this? How does alpha relate to this? You can do it. Remember, this was what kind of test was this? This was a one-tail test. So what does a 0.01 have to do with 2.326? What's the connection there? 0.01, 2.326. What's the connection?
It's the height.
Not really, but it's the amount of area that's in the tail. Exactly. I like it. I'm with you. So alpha is the amount of area in the tail of this, which the book calls the critical z-score. Okay. You guys with me? So alpha is the amount of area in the tail that this z-score makes. The p-value is the amount of area in the tail that my z-score makes. So what's the p-value of 2.74? What is the area in that tail? That's old news. Can you figure that out? The area in the tail of 2.74. How much area is out here? 2.74. I don't see enough wrestling around. You should be grabbing your z-score charts and looking that the hell up.
.0031.
Yeah, 2.74.0.
0. 0. 1.
Read one. I love you guys. Some of you guys are looking at your t-squared chart. It's not going to help you. Doesn't have 2.74. This is a z. So if you look up 2.74, you got to do 1 minus that, of course, what you get to get up here. Are you guys good? And you can do the shortcut. Sure. You guys okay? Has everybody seen that? Is that the right number? I don't know if I have any z-squared charts left. So you look at 2.74, you get 0.9969, so 1 minus that is 0.0031. Of course, the shortcut, you can look at negative 2.74, I love it. This is symmetry. That's the p-value. So now look at a different way to tell. Now, I don't know if you guys remember. Well, actually, let me show you another example because I don't think I pointed this out. Another way to kind of do this test, we already know the answer to this test. We already know. You guys realize that? I mean, 2.74, what was the answer to this? Did it make it into the rejection region? Yes. Therefore, we can reject the null. We can support the alternate, right? We know the answer, but what's another way to tell the answer? My p-value is smaller than my alpha was. It's point... I like it. I requested this earlier. It's 0.003 less than 0.01. Yes. I like it. So if the p-value, and see how this is kind of silly. If the p-value is smaller than alpha, then obviously the z-score is going to be further out. You got a smaller tail because your z-score is further out. This is weird. I'm at Chuck E. Cheese or something crazy. All right. So in real life, there's no freaking alpha. There's no alpha. Right? In real life, it's just they report p-values because every single person reading this article could have a different personal alpha. Well, yeah, to show me evidence, there's got to be 0.001. You know, someone's like, 0.05 is fine. So they just give the p-value, and everybody can make up their own minds about it. Now, in the report, the researchers will state their own expectations, but they just give the p-value. Now, how do I write my conclusion? Did we make it? Let me, I forgot to put over here. What was the thing? We got into the rejection region, therefore we can reject the null, the hope, support the high. That's what we figured out. Now, which one of those was the claim? The high was the claim. Therefore, I'm going to use this language because I have to answer the claim. There's no ambiguity. There's no what word do I use. Whatever the claim was, use that language. So did we make it in? Yes, so we have found sufficient evidence to support. I don't want to see any freaking H's in the conclusion. It's all words. Use your words. Support the claim. And what was the claim? That the average age of a woman at the time of first birth has increased. Don't try to read that. The average age of a woman at the time of first birth has increased. I just get so bored of writing. You guys are like, writing? That's kind of loose definition of writing, John. Yeah, doctor's handwriting without the doctor's help. All right, let's do another one. Just got to do a few of these to really get all the parts down, to see how it all goes together. It does all go together. Okay. Let's try the one on the back. This is one that we all live with every day. I know when I went to grad school, I like to call it a very plastic life I lived. And then you graduate, and then you get a pathetic job. You're like, I'll get a great job and be able to pay the, oh shit. Maybe it'll take a few years to pay off this thing. Be careful, kids. I still remember the first thing I got in the mail, the offer, and I'm like, ooh. And maybe you guys ever watched a show called Workaholics? Yeah, there's an episode where they're like, it's free money, dude. All right, just be careful with credit cards. Have you guys read through this as I was interrupting you over and over again? So this will give you a little more interesting in a few different ways. So what is the claim exactly? Yeah, the debt has stayed the same, so the mean debt is still $906. Now, I just want to say this because I know there's a few people who are going to think this way. We took a sample and we got a mean debt of $882. Someone out there right now must be saying, why the shit are we doing anything? That is less than 906, Jeff. What the hell is all this shit? Right there. Let me help you, Jeff. So if you're thinking that way, don't feel emboldened to speak up. Maybe keep that to yourself. Because what is wrong with that way of thinking? Where did the 882.34 come from? A sample. And what might have happened with the sample I took? I just might have randomly picked some that had less. Right? So when does it become evidence? And that's why it's got to be so far away. Because I allow wiggle room for the natural variations in any random selection I make. I would put money that any sample I take is not going to have a 9 or 6. Even if 9 or 6 is the real mean. It's the real mean. Any sample I take, I'd put money on any of them not having a mean of 906. Hopefully that makes sense. And I'm a teacher, so that means a lot for me to say. Putting any money in anything. So I'm not surprised that it's different at all. The question is it different enough to be evidence that it really isn't 906? So don't just stop there and go, I'm done, dude. What the shit's so wrong with you? I got this stat stuff down. So don't do that. So the claim is it's equal to 906. Which one is that going to be? Oh. Good. It's got a freaking equal sign. It's the most Polish statement we make. What's the H1 going to be? Mu not equal to 906. So what I say earlier, how can you be not equal to something? You could be greater or less. So how many tail tests is it going to be? 2 tail tests. Because my sample could show up on either side and be evidence that H1 is correct. So this is going to be a 2 tail test. Two-tail. Now, so it's a 2-tail test. I don't think we've seen one of those yet. I don't think so. Second interesting thing is, do we use Z-scores, T-scores, or nothing? What do you have to tell me first? Well, why can we do anything? Why is the answer not nothing? Because N, is greater than 30. It's 81. So it's normal enough. Check. That's the first thing you really should know. As long as you say both things, I'm happy. But to be honest, that's the very first thing you should look for. Because if that ain't true and it doesn't say it's normal, you technically can just not do it. See if anybody has the balls to do that. I try to be very careful in a test to make sure that I've got one or the other. But you never know. I'm human. But if I were you, I'd probably say something. I don't think this should technically have to be done. I'm going to do it anyway to cover my ass. Because I am not going to put a problem where if you don't notice, you're wasting time doing it. No. I'm not going to do that on purpose. Right? So N is big enough. And why do I use which one? Why do I use? What do you think?
Because the sample deviation.
Yeah, where did the standard deviation come from? The sample, from a sample of 81. Well, I'm not going to use the letter S to help you. My God, no. you got to pay attention. Where did the standard deviation come from? The sample, so I have to use t-scores. Sigma unknown. That's a freaky looking sigma. That's not much better. Oh well. Sigma unknown and undrawable. All right. That doesn't really change that much, to be honest. I just instead of going all the way to the bottom of the t-score table, I'm just going to stop somewhere based on the degrees of freedom. And then I'm going to put that on my rejection region. That's all. That's not that big of a difference. Rejection region, what's alpha? 0.02. It's a two-tailed test. Degrees of freedom is what? Yeah, 80. So what do we got? Two-tail, 0.02. Degrees of freedom is 80.
6.374.
Yep, cool. You guys see that? You're like, yeah, you're pointing right at the damn picture. 0.374. Now where's it going to be though? Both. There's 2.374. Now please, dear God, don't do this. That makes me worried about you.
Negative.
That one is negative, of course, for the humans. This chart is always positive. Everything's positive. We have to know when it's supposed to be negative. So I got one above the mean and way over there, and I got another one way below the mean. So it's negative and positive. You guys see that? Yes?
Oh, kind of going back a little bit. How did you pronounce the two-tailed testing?
Oh, because not equal to. So how can you show that something isn't equal to something else? You can either show it's bigger, or you can show it's less. Two directions that will show evidence, two-tailed.
That it's like not equal or something?
Yeah, how do you show something doesn't equal something else? You show that it's bigger or you show that it's less. Either way would show that it doesn't equal to. On the other side, why was it a one-tail? Because I'm trying to show something is greater than. There's only one way to show it's greater than.
Yeah.
Bigger. I like it. One way to do it, one tail. Two ways to do it, two tail. No ways to do it, something wrong. Can you put that into words? Sure. Sure. If T star, I like it. T star is less than negative 2.374, or T star is
Greater than.
bigger than positive 2.374. So just further away than 2.374. Then I can do what? If I get in there, I can, then we reject the hoe, support the high. So you only ever reject or fail to reject the hoe. You only ever support or fail to support the high. I like it. So that sets up what's going to be enough evidence. That sets up what far enough away is. And now the next step, of course, is how freaking far did we make it? So what do we know from our sample? What's n? 81. What's x bar?
82.34.
Yeah, 82.34. And then what's s? 107.95. So then what's s sub x bar? The old one divided by square root of
And
the n. I like it. So it's the old standard deviation divided by square root of the sample size. Somebody always asks me, why do we got to do this, Jeff? It's already a sample. It's going to know this is from a sample, sure, but it's the standard deviation of individual debts. I need the one that's the standard deviation of groups of 81 debts. I always have to do this. I don't care which letter you got. Who is it? What? 11.99. 11.99? 990, I guess.
994.
Was it?
994.
1.984?
994.
994. Gotcha. Standard deviation always at least 3 places. Was your weird ass teacher? Oh. And now I just calculate it. Now I very often I just mix these up because at this level it doesn't matter. It's just the measurement of how far away it is. It doesn't matter what you really call it. Yes?
So, wait, why exactly did you reject the loan?
Well, no, we haven't. If we get less than this or greater than this, then it's so far away from 906 that it looks like this guy's wrong, that it isn't 906. It looks like this guy's right. So if we get in there, this is what we can do. So if we don't get in there, we fail at both of these things. I like it. Good. So then how do I calculate this? I calculate it the same way as always. My data, 882.34 minus the 906. We're going to assume that's the real middle. Divided by the new standard deviation. Just about -2. Yeah, I think it's almost exactly -2. Is that right?
Negative 1.97.
Yeah. Look at Jeff earning his money. I know numbers. Now, I'm never going to ask you for the p-value of a t-score. Why was the z-score p-value easy? Because I got a whole chart broken down by all these different z-scores and their areas. The t-score chart is nowhere near as detailed because it's got to be for every possible little degree of freedom up to whatever. In order to be able to do a p-value for a t-score by hand using a chart, I would need a z-score chart for every degree of freedom. Right? A t-score kind of z-score kind of format for every degree of freedom. We don't have that. I don't want to carry that shit around. So, right? And some people go at this point, they'll go, well, why don't we just use a calculator then, Mr. Waller? Well, because I want you to understand, hopefully, instead of just push numbers and see buttons. Okay. Push buttons and see numbers. There. I like it. So what? So do we make it far enough away?
Nope.
No, we made it about right here. Here. Not quite far enough away. It doesn't matter where you put it as long as it's on the right side of 0. And it's also in or out of there. And it's out of there. It's not quite, it's not less than this. So what can I say right now? A little sentence I can say right now. We didn't make it, so we fail to reject the hoe. Fail to support the high. All right, so here comes the conclusion now. So we did not make it in. We failed. So we have not found sufficient evidence. Get in there. So what? Well, what was the claim? Which one was the claim? The hoe. So then you use this language. We have not found sufficient evidence. That's what the word fail becomes. We have not found sufficient evidence to reject the claim. Lord, Jeff, you made one letter out of 2. I like it. To reject the claim that what?
The average student debt has changed.
No.
But the average student has stayed the same.
Stay the same. So basically, from the study, we are not able to say that the credit card debt has changed from the 906. Is that proof that it's still 906? No. That's why we say it the way we do. We have not found sufficient evidence yet. We have failed to reject the null so far. I could do another study if I felt really strongly, and negative 1.97 is pretty decently far away. It just wasn't far away enough. So maybe I take another sample that actually will be far enough away. If my claim is actually true, that should probably happen eventually. Maybe. All right, so now it's your turn. No more Jeff helping you out for a little while.